So in this video, we're going to introduce some very common acute angles where we can calculate the trigonometric ratios of them. So these common acute angles, if measured in degrees, are 30 degrees, 45 degrees, and 60 degrees. If measured in radians, then the measures of these angles when properly converted would be pi over 6 radians, pi over 4 radians, and pi over 3 radians, keeping in mind that the conversion would be to multiply by pi radians divided by 180 degrees. Now, rather than trying to remember everything there is to know about these particular angles, rather I want you to be able to construct two triangles. And the two triangles that I'd like you to construct are known as the isosceles right triangle. Actually, you know what? Let's just start with that one. The isosceles right triangle. In an isosceles triangle, it means that two of the sides are congruent to each other. And by congruent, I mean they are the same length. The only way that that's possible with a right triangle is for us to consider the two legs to be equal to each other. Now, if the two legs are congruent to each other, then the two angles would have to be congruent to each other as well. So, given that they are equal in measure, but also complementary, that lets me know that this angle plus this angle would have to be 90 degrees. Solve this for theta, and we would get that theta is equal to 45 degrees. So 45 degrees here, 45 degrees here. Now, because eventually we're going to be dealing with ratios, it doesn't really matter what lengths I assign, as long as I can assign two of them. So I'm going to refer to this leg as having length 1, and this leg as having length 1. A habit that I really want you to get into is, if you know two sides of a right triangle, immediately turn to the Pythagorean Theorem. So we'll call it a squared plus b squared is equal to c squared. That would be 1 squared plus 1 squared is equal to c squared. Squaring the ones gives us 1. Adding them together gives us 2. Telling me that c squared is equal to 2. That lets me know that the length of the hypotenuse is going to have to be equal to the square root of 2. Combining this with the old SOHCAHTOA will allow us to figure out the sine, cosine, and tangent of this 45 degree angle. So the sine of 45 degrees would be the opposite over the hypotenuse, that is 1 over the square root of 2. Now, me personally, I think it's fine in this form, but if you're interested in rationalizing this, multiply top and bottom by the square root of 2, and you would get the following. This is root 2 divided by 2. Now, from the perspective of the 45 degree angle, that's the same as what the adjacent over the hypotenuse would be. So the sine of 45 degrees is the same as the cosine of 45 degrees, and both of those will be equal to either 1 over the square root of 2, or equivalently, root 2 over 2. This also lets me know that the tangent of 45 degrees, from the perspective of the 45 degree angle, that would be the opposite over the adjacent, that would be 1 over 1, or simply just 1. Once you have that, you can use reciprocal identities to figure out the others. For example, the cotangent of 45 degrees would be the reciprocal of 1, and the secant of 45 degrees and the cosecant of 45 degrees would be the reciprocal of what we got for the sine and the cosine, which would be the square root of 2 over 1. We'll just call it square root of 2. So rather than knowing all 6 of these trigonometric ratios, if you can construct this one triangle, you should be able to determine all of these ratios from that one triangle. This triangle is known as the 45-45-90 right triangle, or the isosceles right triangle. The other triangle I'm going to introduce is not going to start as a right triangle, but we're going to turn it into one. This one is known as the Equilateral Triangle. The prefix equi, meaning equal or same, and lateral, meaning sides. These would be all 3 sides are the same. So that looks approximately like this. So equilateral triangle, all 3 sides would have to be the same length. Now, in any triangle, it's necessary that the 3 angles would add up to 180 degrees. Given that the 3 sides are the same, that means that the 3 angles will be the same as well. So the sum of the three angles would be 180 degrees. So 3 theta is 180 degrees, therefore theta is equal to, dividing both sides by 3, we get 60 degrees. Now once again, I can, because we're going to be looking at ratios, I can label these 3 sides however I want. I'm going to label all 3 sides as having length 2. You'll see why in just a minute. Next, I'm going to take this equilateral triangle, I'm going to cut it. I'm going to cut it right down the middle. I'm going to cut it so bad it's going to wish I didn't cut it so bad. If I slice it right down the middle, like so, then I can consider what's going on only 1/2 of this triangle. And I would get a triangle that looks approximately like this. This would still be a 60-degree angle. For an equilateral triangle, the altitude that we created here is also known as a perpendicular bisector because it's going to intersect at a right angle and it's going to split this exactly in half. So the side that used to have length 2 got cut in half. It now has length 1. Some quick algebra will let us know that the other angle that we see up here is 30 degrees. This one is known as the 30, 60, 90 right triangle, and it covers the other 2 angles that we had on the previous sheet. You know 2 sides of a right triangle. What do you want for Christmas? The correct answer is Pythagorean Theorem, because if you know 2 sides of a right triangle, answer should automatically be Pythagorean Theorem. We'll refer to the leg 1 as A, B is the side we're trying to solve for, and the hypotenuse would be 2. A little bit of algebra here. This would be 4, this would be 1, subtract 1 from both sides, we get a 3. Therefore, B is going to be equal to the square root of 3. Once we have that side, we can label over here as the square root of 3. The way I try to remember this as far as which side is which is that the 30 and the 3 are touching each other. 30 and 3 would be the adjacent leg. Now, once you have drawn this triangle, it is a lot easier to try to figure out all of our ratios. So the sine of 30 degrees, for example, from the perspective of the 30-degree angle, the opposite side would be 1 and the hypotenuse would be 2. Therefore, this ratio would be 1/2. The cosine of 30 degrees, from the perspective of the 30-degree angle, the adjacent side would be the square root of 3 and the hypotenuse would be 2. And from the perspective of the 30-degree angle, the opposite side is 1 and the adjacent side is the square root of 3. That again is from our 9-letter acronym that we use to try to remember which ratio is which, SOHCAHTOA. Now if you want to rationalize the denominator on that, that's totally fine. We can also use some reciprocal identities to figure out the other ratios. Cotangent is the reciprocal of tangent. That'll be root 3 over 1. Secant of 30 degrees would be the reciprocal of the cosine, so that's 2 over the square root of 3. Cosecant is a hoe. That'd be the reciprocal of 1 over 2. So that would be 2 over 1. Now from the perspective of the 60-degree angle, or you can use cofunction identities for these, the sine of 60 degrees, opposite side is root 3, and the hypotenuse is 2. So that'll be root 3 over 2. Cosine, from the perspective of the 60-degree angle, 1 would be the adjacent leg and 2 is the hypotenuse, so 1/2. And then the tangent of 60 degrees would be root 3 over 1. Taking the reciprocals of these, we can determine the cotangent, which would be 1 over the square root of 3. The secant of 60 degrees, which would be 2 over 1. And the cosecant of 60 degrees, which would be 2 over the square root of 3. In our next video, we'll simplify some expressions that contain these trigonometric ratios.